All right. Uh, 2A. How many solutions should we be looking for? 4. How'd you get 4? Good. It's the biggest exponent. What's our list of possible rational solutions here? So plus or minus 1, 3, 7, 9, 21, 63. Okay. There's more. What else do I have? How about 1 over 2, 3 over 2, 7 over 2, 9 over 2, 21 over 2, 63 over 2. There's still more. What else is there? Right? Yeah, so you have each of those then again over 4. So 1 over 4. No. These are all possible rational solutions. There's a whole mess of them. So those all should be listed there. Okay. So then it says, use your calculator to identify the likely real solution. So I went to my calculator, pressed the y equals button, typed in the polynomial exactly as it appears on my sheet of paper, and then I'm going to set my window. What should I set my x min and x max to be? Negative 63 and positive 63. How did you pick 63? Yeah, it's the biggest and smallest number from that list that we just made. Okay, we'll hit graph now and see what happens. So we can't really see a whole lot what's going on because everything happened quite close to the y-axis, right? So if this is negative 60-ish, that's like negative 30, that's like negative 15, that's going to be like negative 7. So maybe negative 7 to positive 7 should still capture everything that I'm interested in. Because again, all I care about is where it's crossing the x-axis. So we'll zoom in a bit. And that looks pretty good as far as the picture goes. Can you guys see the calculator display well enough? If you can't, somebody stand up and just turn the light off. No big deal. So let's look at what those x-intercepts are. So here's positive 1, positive 2, positive 3. This one happens a little bit before that, so maybe I'll call that like 2.8 or something. You just have to estimate though. So if you said 2.9 or 2.7 or 2.6, those are all reasonable, or anything kind of in between those is kind of okay. If you called it 3, that's probably not, because it's not going exactly through 3. We can definitely tell it's less than 3. If you called it like 2.5, that's probably not close enough. But if you were, somewhere in there, 2.6, 2.7, 2.8, 2.9 or so, it's fine. Everybody okay there? All right, let's look at this one over here. So this is negative 1, and this one is negative 2. It looks like it's happening halfway in between. Maybe that's negative 1.5. And then if I look at this last one, it happens just a little bit before negative 3. So maybe I'll call that negative 2.8. Again, if you called it negative 2.9 or negative 2.7 or negative 2.6, any of those are probably fine, close enough. You were estimating there, since it's not at a tick mark. Everybody okay so far? Juan? I changed the x min and x max to negative 7 and positive 7. I just kind of estimated like how much can I cut off and still be able to see that stuff near the x-axis. Yep, the x mins and maxes, Elena. Yeah, just to get a better picture. I just tried to chop off all the stuff that was like empty space. How far I'm changing it down to? Yeah, basically all I'm trying to do is get a good picture of see of what's going on. So I want to start with the biggest picture possible so I can see if there's anything way far out there. And when I've confirmed that there's not, basically I'm just zooming in to chop off all the empty space. So I just kind of estimated, like, okay, this is negative 60. If I cut off half of it down to negative 30, I still have a lot of empty space there. Cut off another half down to like negative 15. Still feels like I have a lot of empty space. Cut again to like negative 7. That looked like it was probably going to be as much as I felt comfortable with cutting. So that's what I did. Does that kind of make sense in what I'm talking about? Okay. All right. So now I'm going to look to see if any of these guys are irrational. So how do I do that? I take the number and I see if it's on my list here in B. Is anything on my list in B close to 2.8? I mean, the closest thing in there is positive 3, right? 7 over 2 is 3.5. It's definitely less than 3, so that's out. 9 over 4 is 2.25. It's definitely more than 2.25, so that one's out. So this one is not on my list. There's nothing close to it. Negative 1.5, that one is on our list, right? So that one tells me it's rational. And if positive 2.8 wasn't on my list, or I'm sorry, negative 2, yeah. So if positive 2.8 is on my list, neither is negative 2.8, right? So those two guys have to be irrational. So I'll just wrote my answer up here. Is everybody okay with how I do that? So basically, I'm just looking to see if the x-intercepts that I found on the graph are on my list of possible rational solutions. So now I'm going to use the bend-bounce-straight theorem. So if I look at negative 2.8, how is that going through the x-axis? That's going straight through. Because it's straight, that means that solution is used one time. How is negative 1.5 going through the x-axis? Where it hits it and then comes back the same direction. That's a bounce. So bounce means it's used an even number of times greater than or equal to 2. So it could be 2 times. Could it be 4 times? Could it be 6 times? Why can't it be 6? There's only 4 possible solutions, right? Now, could it really even be used 4 times? Why not? Yeah, because we have these straights happening also. So this guarantees me using 1 time. If that's 4, that's 5 solutions now, and that's too many. So I can't even have 4. Does that make sense? And then the positive 2.8 was also a straight, so that's used once. Everybody okay there? So if I make my table, it's going to be a very small table for this one. So I'm going to have my rational solution. I'm just going to make a place for irrationals, imaginaries, and total. So my rational solutions I'll list individually, but the irrational ones and the imaginaries, I'm just going to put a blanket spot for them. So I know negative 1.5 is used 2 times. I have 2 irrational solutions, and I have a total of 4 solutions. 2 plus 2 gives me 4, so can I have any imaginaries? No. Okay, so what the table is going to do, it's either going to confirm to you that there are no imaginary solutions possible, or in some cases, like we'll see later on, it will give you the possibility that there are imaginary solutions. It will never tell you for sure if they're there or not, but it'll tell you if it's possible that they're there. All right. So now let's start our synthetic division. To do the synthetic division, I have to use my rational solution. I only have one of those. It's negative 1.5, so I have to use that one. Hello. What is that? That's 48, I think, right? Oh, 42. And that's 63. Okay. And now I could stop and try to factor this by grouping. I think that works, but let's continue on, because I know negative 1.5 can be used 2 times. Let's just do that again. And it did work again. So now let's look at what we have. Because negative 1.5 gives me a remainder 0. That tells me that x plus 1.5 is a factor. And because it gives me another remainder 0, I know it's a factor again. And then this stuff is my other factor. Now this is a little bit of a strange factored result. Why does this look a little weird? Elena? No? So what's weird here is that I have factors that have decimals, but the polynomial they're factoring to has no decimal in it. That's a little bit weird, right? There is a way to rewrite this factored form so that none of the factors have decimals in it. I heard somebody mumble that there's a greatest common factor of 4 in the green factor there. Does everybody see that? So I'm going to factor that out, but instead of writing it as 4, I'm going to write it as 2 times 2. And the reason I'm going to do that is because I'm going to distribute one of the 2's into that first factor and distribute the other 2 into the second factor. So when I do that, 2 times x is 2x, and 2 times 1.5 is 3. This would be your best answer. Again, this is your best answer. So it's not standard if you have a polynomial that has all integer coefficients to write the factors without integer coefficients. That's like a weird thing to do. Not that makes it wrong, but it'd be like saying 2 plus 3 is 15 over 3. It's like, well, 15 over 3 is still 5, but why did you add 2 numbers and get a fraction? Right? Like, it's just weird to do things like that. Joanne? So I factored a 4 out of 4x squared minus 28. So 4 divided by 4 is just 1, so I have 1x squared. And 28 divided by 4 is 7. So that's where the 7 came from. Elena? Well, I knew that I could only use this 2 times. Because they're irrational, I can't use them, so I had to stop. And that's okay, because what I was left with was a quadratic that is perfectly solvable, right? So if I go then to solve this and set each of these pieces equal to 0, I get negative 3 over 2 for each of those. Here, I'd add 7 to both sides and then square root both sides. So that gives me plus or minus square root 7. And if you try to do the square root of 7, you get like 2.6-ish or something, 2.7, something in that neck of the woods. So that was the decimal that we were seeing. Jack. Okay. You should have done that. Okay. And again, that only happens when you do the division with a decimal. Like if you're doing synthetic division with a decimal, you should expect to have to do that. Like I can take a greatest common factor out of the leftovers and push it back into the factors with the decimals in it to get rid of the decimals. Yeah, you would have gotten the same answers. Yes. Yeah. Because again, those 2 factored forms are equal, and they're really, one is no less solvable than the other, right? So it doesn't affect the solving. It's just a matter of like giving an answer that doesn't seem strange. So my analogy before was like, if I asked you to do 3 plus 2, and you wrote your answer as 15 over 3. Like I've added 2 integers, I should get an integer answer back, right? But you wrote a fraction. Now the fraction you wrote is 5. 15 over 3 is just 5. It's the right answer, but why would you write it as a fraction? You know what I mean? The polynomial we're trying to factor has all integer coefficients. Why would its factors have fractional coefficients or decimal coefficients? That seems strange, right? That's why. So that's my quibble there. Does that, as an analogy, does that feel a little bit okay? All right. So let's look at the next one now. What's our answer for part A? 6. Good. What's our list here? Six and 12. And remember, those are all plus or minuses, right? Okay. So let's go ahead and graph this thing then. What am I going to pick as my window? Negative 12 to positive 12. And then I graph. Okay. Can you guys see good enough what's going on there? Not really. Let's zoom this in a little bit. So this spot here at negative 1 and this spot here at positive 2 looks like the 2 things that we're interested in, right? So what can I pick my new window as so I can still see those 2 spots that I'm interested in? Negative 3 and positive 3 sounds lovely. That'll work just fine. Did you have to pick those 2 numbers? No, but they're just reasonable picks. All right. So is everybody convinced there's exactly 2 x-intercepts? What are the 2 x-intercepts at? Negative 1 and positive 2. Okay, on to part D. Are either of those irrational? No. Why not? Because they're on our list, right? Everybody feel good with that? Okay. So if I look at -1, is that a bend, bounce, or straight? That's a bounce. Okay. And if I look at +2, is that a bend, bounce, or straight? Also a bounce. Everybody clear as to how I can tell? You're just looking at the picture, right? Okay, how many times can a bounce be used? Even 2 or more. So could it happen 2 times, right? Could it happen 4 times? Yeah, sure it could. Can you happen 6 times? 6 would be too many, right? Because both of them happen to happen at least twice. If one of them is 6 and the other is 2, that's 8, and that's too many. So 2 or 4 are fine. But we have some possibilities now. So if we make our table, I'll list my 2 rational solutions. I know I don't have any irrationals. I could have some imaginaries. And then my total is 6. So -1 could be used 2 times. And +2 could be used 2 times. 2 + 2 + 0 is 4. But I have to add up to give 6. So how many imaginaries would I have? 2. But I don't know that -1 is used twice and +2 is used twice. Maybe -1 is used 4 times and +2 is used 2 times. In that case, 4 + 2 + 0 is 6, so I would have no imaginaries. And what if instead -1 was used 2 times and +2 was used 4 times? Again, 2 + 4 + 0 is 6, so I can't have any imaginaries. Could both -1 and +2 be used 4 times? No. Why not? That's more than 6. Everybody feel okay there? Now, I don't know which one of these 3 situations is happening, but what I do notice is that it is possible that I have imaginary solutions here. I don't know if I do, but it's possible that I do, unlike the first problem that we just looked at where it was impossible to have imaginary solutions. Jack? If they're both real numbers, how did I know that? Well, if this was used twice and this was used twice, that's only 4 solutions, right? I need to have 6. Where are the other 2 mystery solutions hiding? They'd be the imaginary ones that you're never going to be able to see by looking at the graph. They are invisible on the graph. The only way you're going to find those solutions is by factoring and solving. Now, I don't know that I'm going to have 2 imaginary solutions here, but it's possible that I do. The only way we're going to find out is to do the synthetic division. Okay. So let's start that. 1, -2, 0, -2, -5, 12, and 12. How many of you, when you tried to do this problem, forgot the 0 in your synthetic division? Why did I put a 0 there? Yeah, I skipped the x to the 4th, right? Have to be careful about that. And I'll just start my synthetic division with -1. Did it matter which one I picked? Whether I did +2 or -1? Nah. Now, that worked once. I know it's going to work at least twice, so I'm just going to do it again. Now, I don't know if it's going to work 4 times, but I do know that positive 2 is going to work twice. So I'm going to switch to positive 2. I can always come back and try negative 1 again, but I don't know if it's going to work or not. So I'm going to do the things that I know are going to work before I try things. Is everybody okay with that notion? Okay. So at this point, you could stop. This is factorable by grouping at this stage, but I'm not going to stop here and group because I know I can use positive 2 another time. And that worked. So what I'm left with now is a quadratic. I should be able to factor that quite easily since the leading coefficient of 1, or since the leading coefficient is 1, if it is factorable at all. So rather than try another synthetic division with either negative 1 or positive 2, I'm just going to write down the factored form and see if I can do any factoring at the end. So negative 1 gives me a remainder 0. So I have x plus 1. And it happens a second time, so I'll write down another one of those. Positive 2 gives me a remainder 0, so I'll write down x minus 2. And that happened twice. And then this stuff is x squared plus 3. Can I factor x squared plus 3? No. So we're done factoring. The one thing I would say is that kind of the standard for these problems is rather than writing it all the factors out that repeat, you just use like an exponent. So instead of writing x plus 1 twice, you can just write x plus 1 and then the squared on the outside of the parenthesis. You'll see that quite frequently because, well, mathematicians are lazy buggers, and if we don't have to write down a bunch of symbols over and over again, we'll take a little, introduce some notation to kind of mean the same thing, do some shortcuts. Everybody okay with what I did there, factoring? Okay. So now to solve this, I just set each piece equal to 0. This last one, I have to subtract 3 from both sides. And then when I square root both sides, I get the square root of negative 3. And I know that if I'm square rooting a negative, I have to write an I there. So those are my 2 imaginary solutions that I had, that I knew were possible to get, but I didn't know were coming until I did all the synthetic division and got my factors. Elena? On very rare occasions, if there was like a sum or difference of 2 cubes, you could run into a case where it made a difference which one, like the order you did your synthetic divisions on, but it's awfully rare. It's not usually something you have to worry about unless something starts breaking. And if you really want to, if we have time at the end, we can talk about a situation where that makes a difference. But probably it wouldn't. Yeah. I can think of an example where it would, but it's pretty rare. Okay. The last one, how many solutions should we have here? 7. Okay. And then my list of rational solutions. Let's see, help me out. So 1, 2, not 3 though, right? 4 works. 7 works. 8 works. Is 14 the next one? And then 16, 28, 32, 56, 112, and then 224. Thank you. So again, let's take a look at the graph here. And I'm going to start my window at negative 224 to positive 224. Now, I'm pretty sure this is going to give me like not a lot of information, but I need to check just in case there's like one factor that has a solution that's really big. It can happen. It doesn't in this case, but it could. So I graphed this, and did you see anything happen? What does that mean? Does that mean that the calculator is broken? Did I make a mistake? Yeah, it just means all the action is really tight along the y-axis. That's exactly right. That's a great expression, is tight along the y-axis. So let's figure out what we can zoom this down to. So this is like 200. So that's like 100. It's like 50, 25, 12, and then 6 maybe. I'd feel pretty good about that. Negative 6 to positive 6. Feels like I can zoom in that much and not miss anything. Okay. So I have a good look at what's going on here, but over here I still don't feel great about what I see. Do you guys agree with that? It's hard to kind of see what's going on there. So I'm going to zoom in some more. Yeah, negative 3 to positive 3, that seems reasonable. And maybe we get a better picture of what's happening there. Okay, that did help a lot. I'm glad I zoomed in. Okay, so let's start with this one as it's easy to identify. What would you estimate this value as? 2.6, sounds wonderful. Okay, and then I see another x-intercept here. That one looks like negative 2. And then this x-intercept here, negative 2.6. Okay, everybody feel okay there? Are any of these irrational? Yes, which ones? Both the decimal ones are. How can I tell? They ain't on my list, right? My list has only integers on it, so as soon as I saw decimals popping up, I knew that those decimal ones were going to be irrational, right? So that's good to know. So let's do the bend bounce straight. So positive 2.6 and negative 2.6 are both straights, right? Hopefully it's easy to see that. What is negative 2? It's a bend. Right? You can see how it's kind of like scooping up before we get to the x-axis, how it's kind of scooping down after we get past it. That's what you're looking for a bend. How many times can a bend be used? Odd number, right? So 3 times. Can it be used 5 times? Yes. Could it be used 7 times? No, because we have those 2 straights still, and that would be too many. Everybody okay here? Okay, so let's make our table. So we have negative 2, we have our irrationals, and we have our total. So 3, 2 of those. For 7 total, I'm missing 2, so I could have 2 imaginaries. But if this is used 5 times with 2 irrationals, that's 7 already, so I couldn't have any imaginaries in that solution, or in that situation. So this one could have imaginaries, but it might not. We're not sure yet. But it's possible. Okay. So we'll start our synthetic division here. Okay. So that worked. And I know I can use this at least 3 times. So I'm just going to keep on going. Now, if this failed for me for whatever reason, obviously I'm going to stop and go back and look for my mistake because it shouldn't fail. It's probably you dropped a negative sign or something. That's frequently a place where students make mistakes when they're doing these synthetic divisions. So you just have to be a little bit careful there. Okay. So again, I got remainder 0 each of those 3 times I tried to do this, so things are going well. Now, what I notice here is that I have a degree 5 polynomial left over, right? But look at where the zeros are. I'm sorry, degree 4 polynomial. Look at where the zeros are. If I write this out, that's my leftover polynomial. That's something that, although it's not quadratic, it is in the quadratic form. This is something I could factor like I did in last semester using my factoring tree. So I could try another synthetic division with the -2. I'll tell you right now, it's not going to work. This is one where you'd have to use your previous factoring tree knowledge to factor this one. So what I'm going to need now is 2 numbers that multiply to give me -28 and add to give me -3. Elena. -7 and +4. Good. And because the middle term of this quadratic form is x squared, when I factor this, I get x squared -7 and x squared +4. Could I factor either of those anymore? X squared -7 or x squared +4? No. X squared -7 isn't a difference of 2 squares because 7 isn't a perfect square. And x squared +4 isn't a difference of 2 squares because there's addition going on in between. It's not a subtraction problem. So this is my best factored form. That's as far as I can go. And now to solve this, I'm just going to set each piece equal to 0 and solve. So these first 3 are really easy. I just get -2. Here I'll add 7 to both sides, and then when I square root both sides, I get plus or minus √7. Here I'll subtract 4 from both sides, and when I square root both sides, I get plus or minus the square root of -4. Well, because I am square rooting a negative, I know I need to use an I, and then the square root of 4 is just 2. So plus or minus 2. And there's my final answer. Everybody okay there on this? Feel a bit better doing this process? Good.